Good morning to everyone. My name is Rafael Murrieta. I am a researcher here in CIMAT. And today we are very glad because we have as a speaker Professor Seth Hutchinson. Let me briefly read a short biography of Seth. Seth Hutchinson is professor and Kuka chair for robotics in the School on Interactive Computing and the Georgia Institute of Technology, where he also serves as executive director of the Institute for Robotics and Intelligent Machines. His research in robotics spans the areas of planning, sensing, and control. He has published more than 200 papers on those topics and is co-author of the books Principles of Robot Motion, Theory, Algorithms, and Implementation, published by MIT Press, and Robot Modeling and Control, published by Whaley. Hutchinson is president of the IEEE Robotics and Automation Society. He currently serves on the editorial board of the International Journal of Robotic Research and chairs the steering committee of the IEEE Robotics and Automation Leader. He was founding editor-in-chief of the IEEE Robotics and Automation Society Conference editorial board from 2006 to 2008, and editor-in-chief of the IEEE Transaction on Robotics 2008-2013. Hutchinson is an emeritus professor of electrical and computer engineering in the University of Illinois at Urbana-Champaign, where he was professor of ECE until 2018, serving as associate head of the undergraduate affairs from 2001 to 2007. He received the PhD from Purdue University in 1988. Hutchinson is a fellow of the IEEE. And you know what is most important, Seth had an excellent research, and he has been collaborating with people in Mexico for a long time. He has spent time in the Tech of Monterrey, in CIMAT, in Sinvestar Saltillo. He was a keynote speaker in MICAI in 2019. And we are very glad to have here today. Please go ahead, Seth, with your talk. Thank you very much.
Thank you, Rafael. It's always good to interact with my Mexican colleagues. Today it's sad because I'm interacting from Atlanta and not face to face in Zacatecas or Guanajuato or some other wonderful Mexican city. As Rafael mentioned, I have a lot of collaboration with my Mexican colleagues, and some of the best stuff that I've done in my career has been done in collaboration with Rafael in particular. A lot of the stuff that I really like, which I'm not talking about today, but a lot of the things in pursuit evasion that I find really to be fun and interesting have been done with Rafael and students that we've worked together with over the years. So it's a treat to have a chance to talk to you guys, even if it is remote. So what I'm going to talk about today is some work that happened at the University of Illinois over about a 5 to 7 year period. And it really, I think this is sort of wound down now. So I'm going to talk about this retrospectively, give my thoughts about it after the fact. Where are we now and what did we learn? Because we learned a lot over the period of time. A lot of people were involved in this project over the years. The people that you see on this PowerPoint slide, these are the guys who did most of the real work. And in particular, Alireza Ramazani was a postdoc with us at the University of Illinois when we did this work. He had been a student of Jesse Grizzle. And if you know the walking robot literature, then you certainly know Jesse Grizzle. And we found out something that I thought was interesting and I hadn't really thought about very much before, that the same kind of mathematics, the same kind of modeling tools, the same kind of engineering that you use when you design walking robots is super useful to design robots that are doing flapping flight, in this case, like our bat robot. And so we kind of learned that there are a lot of parallels between locomotion strategies regardless of what kind of locomotion it is. There are a few mathematical concepts that show up over and over again, a few kind of design techniques that show up over and over again when you work on locomotion systems. And we were lucky to have Ali Reza with us during this period because he brought a lot of expertise from the legged locomotion world. John Hoff was my PhD student at the time. He's just now finishing a postdoc at the University of Illinois. And we're not sure where he's going next, but I think it's going to be somewhere in the Seattle area because that's where his family is headed. And then Soonjo Chung was a professor of aerospace engineering at the University of Illinois. He's now at Caltech, also a professor of aerospace engineering, or whatever they call that department at Caltech. So all of us are leaving or have left the University of Illinois by now. This is how I want to approach the topic today. I don't want to talk about this just as a purely engineering talk about, you know, suppose you put 5 engineers in a room and ask them to design a bat robot, what would it be? That's not the way we thought about this project from the beginning. And I don't even think it's a very interesting way to think about this project when you look back at it. I think a more interesting way to think about this kind of work is from the perspective of bioinspiration or biological inspiration. A lot of people are working today and have been working for a decade or two in biologically inspired robotics. And the people who work in bio-inspired robotics are not looking at bio-inspired robotics in the same way. In fact, there's a spectrum, and here I've illustrated the 2 endpoints on that spectrum. There really are a number of people doing biorobotics, and the bio-inspiration is not very deep, right? It's, I saw an animal, the animal did this thing. I should build a robot that could do that thing. And in this case, that thing would be flapping flight. It's not a very deep inspiration. It turns very quickly into the engineering problem solving approach that I mentioned just seconds ago, where you have engineers in a room saying, how can we design an engineered physical system that replicates this biological behavior that we saw you know, at a zoo or in a movie or something. At the other end of that, that spectrum, you have people who are very serious about the biological motivations. People who are studying the animals very closely, maybe even dissecting animals to look at the specifics of bone structures and musculoskeletal connections and how all these things go together to make the biological system work, and who try to replicate that. Right? So you have people that are working on robots that have muscle systems that are meant to mimic physical muscle systems. Quite often this is done with pneumatic actuators, for example. So you can place yourself anywhere on this spectrum, from very strong to very weak bioinspiration. And the question that comes up, I think that's interesting, is where should you be on this spectrum? Right? At what point should you move away from looking at the animal and start thinking about engineering? Or should you ever do that, right? Should you focus on the animal and its capabilities and its biological and mechanical structure all the way to the end? So this is how we looked at the problem for this biologically inspired robot bat. It was first to step back and ask, you know, what are the right questions, right? What should we even be asking about when we look at the biological creature? And here are the first couple of questions, right? Should we try and really build a robot that is a replica of the biological animal? Or should we abstract away a lot of the details of the bat very quickly to a simpler kind of mechanical structure? And this raises immediately the question, well, then what are the salient features of bat-like flight, right? If you want to capture this kind of behavior, what are the right features to look at? A question that I thought would be really important, and it is important, but not nearly as important as I expected to be, is what's the role of geometry versus dynamics? And the question that I thought would be really interesting is, can you do flapping flight based purely on the geometrical structure of the robot and the wings and the trajectory? can we ignore dynamics? If I study bats as they fly, and if I really understand the geometry of what's happening in the bat wings and the bat body and the trajectory of the body, is that enough? Or do I need to worry about the Lagrangian dynamics, right? When you flap the wings, you exert forces on all the joints that interact with one another. Do I really need to worry about aerodynamics if I have this full understanding of geometry? And it turned out that the answer is, yeah, you really have to worry about all the dynamics in the end. Nevertheless, you can get pretty far just by studying geometry, right? And in the talk today, I'll show you how far you can get and why you have to change from a geometrical perspective to a dynamical perspective at some point. And then finally, questions about control, right? Once you have a physical object that you've designed and built, once you have the mathematical models for how that object behaves when it interacts with the environment, how do you control it? And there are a few things that are obvious just at a first passing thought, right? You don't have to think very deeply to realize that you will not be able to do real-time control with exact inverse dynamics, right? You won't be able to solve the inverse aerodynamic problem in real time. So can you do things, can you cheat basically? Can you do the kind of cheating that control theorists do? For example, can you do linearizations that will get you closer to the kind of control that you need to get the behavior that you want? And then finally, what about data? Data has been, in the last 5 years, finding its way into robotics quite a lot. In fact, if you look at the topics that are discussed at ICRA last week, it's not the #1 topic, but I think it's number 2, 3, and 4. The topics that are related to machine learning in their different manifestations. And so how can we do learning, if you like, on the physical system to inform our design and programming of the robot system, of the biological system rather, to inform the robotic design and the robotic control? And this is the way I'm going to approach those questions in this talk. So I'm going to begin just by looking at the bat, and by the bat, I mean the physical animal as it flies. What can we learn? What can we infer from looking at the physical animal? From that, I will posit some constraints on the design, and in particular, some constraints on the topological structure of the design. Once we settle on a topological structure, then there are questions about what should be the design parameters, right? What should be the values of the various kinematic parameters that go with the topological structure? Then once you have that, how do you optimize trajectories, taking into account aerodynamics, and then the control design? Some extra stuff if we have time to talk about how we did a little bit of extra machine learning stuff on the back end to improve all that. But we'll see if we have time for that. I seem to be rambling more than usual, so we may run out of time early today. We'll see. All right, so let's look first at biology. Here is a cartoon of the bat's skeleton superimposed on a photograph of a bat. This is taken from the work of Sharon Schwartz and Kenny Breuer. We did a lot of collaboration with them in this project. They study the bat as an animal from the perspective of biologists, but also from the perspective of engineers. And they have done some really beautiful analysis, some of which I'm going to talk about in the next few slides, to really understand what's happening when the bat flaps its wing and flies. But if we look just for a moment at the physical structure of this animal, it's complicated. This is much more complicated. I think it's fair to say that there is no robot at the moment that has a kinematic complexity equal to or larger than what a biological bat has. There are basically about 40 degrees of freedom. Some of them are passive that respond when other degrees of freedom move. Some of them are active. Some of them are ball and socket joints. Some of them are revolute joints. In addition, just to the structure of the various, you can see various kinematic trees that are coming out of the torso. In addition to that, there's the added complexity that nothing is rigid in the bat. All of the bones are flexible. Of course, the membrane that goes over these bones is flexible as well. There's far too much complexity here to attempt to build a robot that has the same kinematic structure. There's no way we're going to build a robot that has 40 degrees of freedom and also is comparable in size to a biological bat. Right? So we're going to have to make some simplifications. What are the right simplifications to be made? The first thing that is useful, right? When you start thinking about how can I simplify the structure of this this biological bat, how can I extract high-level geometric descriptions? The first thing useful that you might recognize is that what you see here in terms of the skeletal structure of the bat is almost exactly the same as the skeletal structure of a human from the shoulder to the fingertips. Less fingers, but you'll see a shoulder, an elbow, and then 3 very long fingers, basically with the same topological structure as the human hand. And why is that interesting? It's interesting because roboticists have been studying grasping in the human hand for a long time. And so we have a lot of tools in the robotics world for analyzing the robot grasping, for example. Right? We know a number of ways to approach that problem, and we can apply those directly to what's happening with the bat. And in particular, we can investigate these ideas of synergies. How do we do that? Well, step 1 is collect a bunch of data about the biological animal as it flies around. Right? And so here you see a bat flapping. This is actual video from Kenny and Sharon's group. What you do is, this is taken from below, by the way, I don't know if you can tell. There are 2 markers on the belly and the chest of the bat, and then a bunch of markers on the wing. And you put those this robot into a wind tunnel with a motion capture system, and you collect data of the bat flying in the wind tunnel. And in this case, I think they used 17 markers, computed some inverse kinematics to get joint angles for the joints in the skeletal structure. The flapping frequency was about 10 hertz, 9.5 hertz, it says here. And then they did a principal component analysis, or essentially a PCA analysis. It was they call it proper orthogonal decomposition, but to us, it's more familiar as principal components analysis, to figure out what's happening with this bat as it flies. And this is the data that comes out. This is not exactly true. When you look at these 3 plots, everything looks so perfect. In fact, to get these plots to look so perfect, you have to do some normalization, you have to do some phase shifting and so forth to get things to line up visually. But what comes out very quickly from the PCA is that there are really only 3 kinds of interesting things that are happening when this bat flies. There's synchronous flapping of the left and right wings. There's some asynchronous mediolateral motion, which basically means the wings fold in and out, right? So I don't know if you can see my arm well, but you get this folding motion of the wings. And then finally, the tail, the hind limbs move independently. So this is it. This is the really everything that's interesting about the wing structure of the bat can be grouped into one of these 3 kinds of motion. And if you start there, you're now in a position to think about what should be the topology of the kinematic structure of a robot if the robot is meant to replicate these 3 kinds of motion. And so the challenge is this: replicate those 3 kinds of motion, synchronous flapping, wing folding, dorsoventral leg movement, but with a lot of constraints. And the constraints are, they're hard for engineering, for engineers. Low weight, low power consumption, small size, structural stability. And basically the hardest things about this design come from the fact that when you throw it into the air, it should fly by flapping its wings. If it's going to fly by flapping its wings, if you know much about aerodynamics and Reynolds numbers and this sort of thing, it means it can't be very large. If you don't want it to fall out of the sky, it can't be very heavy. It has to be low power because it has to carry its own power source with it. And if you have to put a giant battery on it, then there's no way for it to fly. And then finally, all these things fight against the structural stability, right? So when you flap the wings, you don't want them to break, right? You want them to be able to withstand whatever aerodynamic forces are applied when the flapping occurs. This is what the structure looks like that we arrived to, right? So this is an a posteriori look back at the design that came out after some trial and error. The mechanical version of that is here. This is a Watt mechanism that you see. Basically, these 3 degrees of freedom are coupled so that when this linear actuator moves back and forth, these 3 revolute joints move in response as shown. And this gives us a way to fold the wing and the fingers in and out, coupled together, right? So this captures the the tight coupling that you saw a few slides ago. That really there's only 1 degree of freedom happening when this robot folds in and out. Can we build that into the mechanical structure? The answer is yes, and here's a mechanism that does that. This 6-bar linkage that you see is called a Watt mechanism. It's a parallel mechanism, and the reason it's nice is the fact that it is a parallel mechanism, and that gives it structural stability to support forces perpendicular to the wing, right? So when the air pushes up, this parallel mechanism is able to resist that, and it doesn't bend or break. It's all done with carbon fiber tubes to get extra structural strength. And then there's an, excuse me, an encoder equipped spindle drive at the back that moves the tail, the legs independently up and down. Right, so here's the way it looks. On the top left, you just see the robot moving. It's unactuated here just to see what the degrees of freedom are. And in the bottom right, you can see what are the actuated degrees of freedom and how can we control them. Right? So you see, as the thing on the left or on the right, as those wings move, it's one actuator, one linear actuator that's moving. And as it moves, the entire shape of the wing changes in response. All right, so let's talk about now that you've got the topology, how do you design the kinematic structure, right? What should be the size of each of those links, and what should be the offset angles? And then once you have the physical structure designed, what should be the trajectories or the actuated degrees of freedom in order to achieve flapping flight? So here's just a very quick, and it's not important at all to remember any of this stuff. Just remember the groupings. You have 3 actuated degrees of freedom. You can flap the wings, you can fold the wings, and you can move the tail. You have 3 passive degrees of freedom that respond, right, that are coupled with the actuated degrees of freedom, and you saw those a couple of slides ago. And then you have a pile of kinematic parameters that you have to design. And you can think of these, if you're a manipulator person, you can think of these as being just sort of fancy versions of Denevit-Hartenberg parameters. Right? There's really not anything more happening here than that. And so the questions are, what should these link parameters be? Right? What should be the angles between the fingers? Right? And these are constants, part of the mechanism once you design. So how do you decide that? And the answer is this. We're going to decide what those parameters should be so that the geometry of the bat wing is the same, I'm going to say the same in quotation marks, to the geometry of the biological bat during the flapping flight. Now, obviously, it's not going to be the same in a point-to-point exact transformation way. We want to capture the sameness in some abstract way that captures the salient aspects of the geometry. So we have to learn what the salient aspects are. And how are we going to do that? Well, we have markers on the bat. You saw those a couple of slides ago. We can, for every possible design that you can imagine, you can immediately write down where would be the markers on the robot that correspond to these markers on the bat. And so now you can look at motion capture studies of the bat. And this one's here just because I think it's really beautiful. You can see what's the trajectory of each XYZ point on the biological bat, do some sort of principal components analysis on that to reconstruct the shape of the wing as it evolves over time, and then try to design the mechanical system to replicate that as best as you can. And the way to do that, or at least the way that we did that, was to place markers on the robot. These are not real markers because this is during the design stage, right? So it's where the markers would be if the robot were designed in a certain way. Collect up for a particular trajectory the positions of the markers as a function of time, right? So each row corresponds to a time sample, and each column corresponds to the position of a particular marker. And then we do that for both the biological bat, where we just capture that data and store it, and then for the simulated design that we're looking at any particular moment. That matrix, it's a big matrix, and it doesn't have nearly as much information in it as it has entries. So what can we do? We can do a singular value decomposition of that matrix, truncate the singular values. I think we used 2 or 3, 3 I think in the end. Set the rest to be equal to 0, and then reconstruct the parameters of the motion and of the geometry in terms of that truncated singular value matrix. And then the question is, what should be the design parameters for the robot such that the truncated matrix for the robot matches very well the truncated matrix for the biological organism, for the actual bat. How do you do that? First, there's a bunch of parameterization, a bunch of design constants for the mechanical structure, a few time varying parameters for the trajectories that we just modeled as low order polynomials, 5th order it says here. Now you can reconstruct, if you know the trajectories, you can reconstruct the trajectories of each marker, both for the bat and for the robot. And it's just an optimization problem, right? So minimize the Frobenius norm between the 2 truncated data matrices over the trajectory, where the optimization variables are the constants of the mechanism and the coefficients of the polynomials for the trajectory. And if you do that, this is the kind of result that you can get. On the right-hand side is a reconstruction of the flapping flight of the biological animal, right? So this is reconstructed by triangulating the data that we got back from motion capture from Kenny and Sharon. And on the left is the biological structure. You can see the wing, the watt mechanism, the parallel mechanism folding in and out as the flapping occurs. And so this is the moment when I thought a few years ago, if you build a robot and throw it into the air, it should fly because geometry should be enough. And at this moment, I will tell you, I was just really, really wrong. At this moment, if you throw the robot into the air, it crashes almost immediately and quite spectacularly. And you realize that that hypothesis just doesn't work. Excuse me. And so as a robot motion planning guy who had studied geometry for a very long time, I was quite disappointed to find out that now, as an old man, I had to go back and learn aerodynamics and Lagrangian dynamics of the system, which I'm going to talk to you about in a moment. But first, I'm just going to show you quickly the prototype hardware. So here's the robot. There were a number of variations on this. Just to give you a sense of the difficulty of the design, there's a lot of stuff in this robot that have nothing to do with the mechanical flapping, right? There's an IMU, there's data storage, there's a microcontroller, a lot of avionics equipment that goes in addition to tiny motors and encoders and all of that stuff. You've seen some version of this a minute ago. I will tell you that the silicon membrane that goes on the wings, that was a trick to figure out. Basically, we hired a couple of really smart students from material science, and they figured out how to make that membrane. And in the end, we got something that was very flexible and also very strong. So you see somebody at the bottom right poking it with a probe, and it will resist forces quite nicely. And what you get when you do this is something that is, it's similar, at least to a first order, to what happens in biological bats. Namely that when the bat flaps its wings, the membrane of the wing deforms, it fills up with air. And then at the bottom of the downstroke, the membrane pushes that air out. And you get this force amplifier in the aerodynamic world that comes just from these passive dynamics of the membrane structure. And so it's a very cool property that we were able to exploit, I think, as well in the robot design. So now I'm going to talk really quickly about trajectory design. And the thing that I think is most important about the next bunch of slides, many of which I'm going to skip over very fast because the details are not that important. It's this. In the end, you have to figure out something about aerodynamics and the Lagrangian dynamics of this system if you want the trajectory of the robot to behave well. And basically, there's a line that you draw, right, on the spectrum from data-driven approaches to engineering with sophisticated mathematical models approaches. And where do you draw that line is an interesting question. And the answer for us is you draw that line right here, right after you've done the geometry and designed the mechanism. The question immediately should come up, well, why? Why do you draw the line there? And the answer is really simple, because at this moment, we have used everything that we can measure. So we don't have the capability to measure what's happening in terms of the structural biological bat as it flies, how much force is being exerted on the shoulder or on the elbow or on the membrane. We're not able to measure any of those things, right? In order to measure those things, you would have to have a pretty sophisticated sensor pack on the bat, the biological bat. And at the moment you start putting all this garbage on the bat to measure what it's doing, the bat becomes completely uninterested in doing anything, right? So, so here, little bat, I want you to carry around this heavy sensor package so that I can measure what you're doing when you fly. And the bat says to you, I think I would rather just not fly because this stuff is painful and too heavy, right? And so there's a real limit. We didn't really have this conversation with the bat. This is all hypothetical. But there's a real limit to what you can measure. And therefore a limit to what kind of data-driven approaches you can use based on the kind of data that you can obtain. So at this moment, we ran out of data and we switched to mathematical models. And the mathematical model is the usual one. You have a system that's just defined in the configuration space in the usual way. You can think of the torso of the bat as a rigid object. So the usual rigid body dynamics are there, X, Y, Z, and 3 angles. There are some passive joints, and then there are a few active joints. And in our case, just a few, right? The 3 that I showed you, but for both sides of the robot. So half a dozen actuated degrees of freedom. And in the end, you can bundle those up nicely into a configuration that has a bunch of things that are configuration variables over which you have no control at all, and a few configuration variables over which you have complete control, right? So you have complete control over the actuated degrees of freedom. They respond to the electricity that you send to the motors. The nonlinear model of the dynamics, it's pretty similar to what you see when you look at robots. Let's see if I can do this. Yeah, so you have this stuff, which is your usual Lagrangian dynamics of the robot, right? mcq dot gq, that's accelerations terms and inertia matrix, Coriolis terms and gravity terms. And then you have this, which is the torques that you put in to the motors, right? So all this stuff is in any textbook on robotics. But you have now also this stuff, these forces that come from aerodynamics. And the problem with the forces that come from aerodynamics is that they depend on the accelerations and the velocities of the configuration parameters. So you cannot decouple the aerodynamic forces from the input forces and torques, or from the configuration parameters in a nice way. Right? So the torques going to the motors, you can decouple that stuff from what's happening in terms of accelerations and velocities. Right? I'll put in more electricity and I get more torque, and that's that. But for the aerodynamic parameters, the aerodynamic performance depends on what the wing is doing in a way that doesn't give you that clean decoupling. Right? So I'm going to skip this, but it's just to say that you can rip those equations apart. You can use a very simple model of aerodynamics. And this may not look very simple, but it is. I'm modeling each wing as a big flat rectangle so that I can easily integrate the forces over the surface in a way that is computationally super tractable, but not particularly accurate in terms of what's really happening. And then I'm going to do trajectory planning, which is put in the variables for the actuated degrees of freedom and see what happens. I'm going to skip this stuff. It's just some nuances about how to deal with constraints to keep this robot flying on the right manifold. This is the part that is the part that's interesting, I think, once you get past the sort of mathematical modeling stuff, is how do you do the trajectory optimization? And the way we did it was just numerical methods, right? So we have the models that I just breezed over, but you can write them down, you can solve them numerically. And now you enforce some constraints, right? You want stability, periodicity of the motion. You want to make sure that the unactuated coordinates don't correspond to trajectories that fall out of the sky. You'd like to minimize the energy that's being used. And you can do all this stuff in a straightforward way. We did this basically with shooting-based methods. And here's the kind of trajectory that comes out. That comes out of the optimization process, right? So what you're seeing here is simulation. And so now the question is, if I can simulate this, right? If I can optimize the trajectory, and this is what the simulated system looks like. Well, the simulated system is pretty simple. Right? It has just like 7 degrees of freedom to it. So when I try to make my real robot follow this trajectory, what do I have to do? And the answer is you have to design a controller to track that. And the way we do control design, I think I'm not going to succeed to teach you about the method of Poincaré in 5 minutes. And if you already know the method of Poincaré, then that would be 5 minutes that are wasted. So let me just tell you this. You can think about dynamics as being continuous, right? A system evolves continuously over time, and you can write those equations down. I showed them 15 slides ago. I showed you the dynamic equations of the system. Another way to think about the dynamics is to think, let me just look at the system at discrete moments of time. And in legged locomotion, this is a very popular thing to do. And the discrete moment of time when you look at a running robot might be the moment when the foot hits the ground, right? So I'm only going to look at the robot when the foot hits the ground. And then the next time I look at the dynamics, it'll be the next time a foot hits the ground. And we can do the same kind of thing with flapping flight, where we look at the system dynamics at the bottom of the downstroke, for example. Or you can pick any moment that you like. We picked the bottom of the downstroke. And so when I do this controller, I'm going to look at, here's where I am right now at the bottom of the downstroke. What do I need to do to the control input so that after the wings go up and come back down again, my system will be better than it is now in terms of its dynamics? Or I want to improve some kind of characteristic, get closer to a desired trajectory, for example, right? So that's how I'm going to think of control design. And the way to do that, let's skip this, is just to say, I can take that thing, that mapping from this moment in time that maps me to where I will be the next time I hit the downstroke. That's called the Poincaré map. I can linearize the Poincaré map, right? And there's some mathematics involved in that, but really, in the end, it's just a linearization of this complicated map. The system dynamics that are linearized are shown in green, but really they look just like any other x dot equals ax plus bu, where the control input u is here delta bk. And so I can do feedback controller design. And in fact, that's what we did. We did an LQR design where we linearized about the desired trajectory. And so it's disappointing, I think, in some ways. Let's see if I can do, where did it go? Pointer options. This matrix K, you know, in an ideal world where computers are super fast, you would dynamically compute this gain matrix by solving the LQR problem in real time. But in our world, all those equations are much too difficult to solve in real time on the processor that lives inside the robot. So we did a static control design around the linearized version of the trajectory, basically. And what does that mean? It means, I'll show you a flight test. So here's Alireza throwing the bat robot, and you see it flies, and it's just beautiful. You should just watch it and absorb the beauty. All right, and so one of the things that you'll see about our experiments, where we place the nets is never right. We always expect the robot to crash, and then it always flies further than we expected. And so we have to land it someplace that's not on the net. So let me see if I can show you that one more time. The important thing that I want you to notice, I'll show it to you one more time. Watch Alireza throw that robot. He is a very skilled robot thrower. Why does that matter? It matters because we linearized the desired trajectory in order to design our control system. And if you're linearizing about a desired trajectory when you design the controller, it assumes that design approach assumes that the robot will be, when it's actually behaving in the world, somewhere near the desired trajectory. If not, the linearization doesn't make any sense, right? So it's important that you start this robot with an initial trajectory that matches very well the trajectory that you used for the linearizations, right? And so part of the reason that this approach works so well in practice, so when you look back at this result, this is a really nice result, and it's controlled, right? It's not a robot that crashes at the end. It's a controlled soft landing. The reason it works well is because we linearized about a trajectory, but then we made sure that the robot started out on that trajectory. And so there's some engineering work and also some work at the time of doing the experiment to ensure that you match the conditions that you designed for. Right? So I'll show you this one more time. And again, you see that we're far too optimistic in the placement of the nets, and the robot flew much faster and further than we expected, as usual, smashing into the wall. So that's what you get using a very simplified aerodynamic model. I've got about 5 minutes left that I'm going to spend talking about how to do even better than that. You can do better if you have better models of the aerodynamics and of the control surfaces that you use to control the aerodynamic response. So instead of just modeling each wing as a big flat surface, I'm going to make the control surfaces slightly more interesting, give them a few more degrees of freedom. That means I need to be able to somehow understand the relationship between those control surfaces and the aerodynamic forces that result. In order to do that, I'm gonna do data. I'm gonna do data collection, right? And really use some machine learning kind of approaches, not the deep neural network kinds of approaches, but just the parameterized model and parameter estimation kinds of approaches. Then for the optimization, instead of doing the numerical integration stuff and numerically calculating gradients that I showed you, that we use for the methods that I just showed you, we used here direct collocation, which means you make some pretty strong assumptions about how you can parameterize and represent the trajectories. And then we get out desired altitude and orientation, and we can do much better now and actually plan maneuvers that take us from initial conditions to cruising altitudes instead of relying on an engineer to match up the initial conditions perfectly. Right? So here's a slightly more complicated model of the robot. more degrees of freedom in the wing and in the tail. And then we strap that robot onto a force torque sensor, basically a load cell now, so that we can measure the forces and the torques that come out as a function of things like the flapping frequency. Here are some experimental results that we get. These results come from motion capture on the robot compared to the simulation. Simulation shown in blue, motion capture shown in red. And something that's cool that almost never happens in real robotics is that our simulation, you can see the blue curve and the red curve are not the same. And for one of the few times in my life, the fact that the simulation wasn't that great turned out to be good for us. Why did it turn out to be good for us? Because the simulation neglected some of the physical interactions of the robot with the world, in this case, the aerodynamic forces. There's a low pass filtering kind of effect that happens when you throw this bat into the world and it starts to fly. And so these higher frequency dynamics that you see in the top plot get essentially filtered out by the physical mechanics of the system. And that turned out to be helpful in terms of controlling the system in the end. Often you get high frequency dynamics that are excited when you do certain things that are really problematic. But in this particular case, it was the opposite. The high frequency dynamics got damped out by the physical system. I'll show you just a quick video that shows you, here's the load cell that we used to do the experiments. And then when we did the trajectory optimization using the co-location method, we're able to plan these kinds of trajectories. And here's the robot actually doing this, following that planned trajectory to gain altitude. And now we've become more sophisticated in where we place the nets. We're placing nets vertically now to stop the robot as it flies. I think I can show, let me go back and show you one more time the launch. So you can see that the robot's gaining altitude as it flies until the moment that we turn off the wings and it coasts gently into the net. So we have a lot more control now and a lot more sophisticated trajectory planning algorithm as well. Well, it's 1:48. This is a good time to stop. Just looking back, here are the concluding remarks. When we're going from biology to engineering mechanical systems, what kind of data that you can get plays a big role in how the design process evolves. And for us, basically, we were able to look at and collect data for all the geometry stuff and none of the dynamics and the force-based stuff, right? So that's where engineering stepped in to take over from biologists. And then we showed that once you have a physical design of the system, you actually can go back and collect data for the dynamics, right? We can't measure the dynamics of the biological system as it flies, but once we've designed and implemented the robotic hardware, we can go back and collect dynamic data for the mechanical hardware. And so you can do sort of a two-stage learning approach where you do learning of the geometry from the biological system, then mechanical design, then learning the dynamical parameters of the system that you actually built in the next stage to make the optimization more realistic in the end. And I think I will stop right there. And if there are questions, I'll try to answer them. I don't know, Rafael, the right way to ask questions, if people can speak or if they should type them into the chat. Whatever is best, I'm happy to go along with that.
Hi, thanks very much, Seth. Yeah, they can do either. They can ask speaking or write down either in Spanish or English, and we'll get it to you.
Yeah, if you write them in Spanish, I will understand at the moment, Rafael or Uziel translates them into English.
That works.
Yes, I think people may ask questions by writing in the chat or speaking. Seth, for starting, I had a couple of questions.
Sure.
One is, what is the thing that you are optimizing? Are you optimizing energy, or what is the parameter, the criteria that you are optimizing in the trajectory planning?
So in the first part, we were really, everything came down in the end to satisfying the constraints that the center of mass should not be decreasing in height, right? So the overwhelming, I think, aspect of the optimization was to keep the altitude high enough so it didn't fall from the sky. And then secondarily, an energy minimization. I'm not sure the energy minimization really had that much effect because in the end, the robot's just sort of flapping at its maximum, maximum bang bang kind of control almost for the flapping. In the second part, we were optimizing to track a particular trajectory with a target altitude, right? So we wanted to go from some initial launch condition, to some steady state height. And so we were optimizing to gain altitude over time.
I see. And you know, how similar are the trajectories for our real bat trajectories? Are they somehow similar or are totally different?
So this is a really interesting question. We made some, I think, pretty stupid assumptions at the beginning. And I'll say I don't, because my colleagues are really smart and they make good assumptions. Here's, I think, where we went wrong. One of the places that we went wrong. We started working on bats because we wanted to have a robot that could fly and have really agile trajectories, right? So it could really adjust very quickly its direction, for example, and do aerial maneuvers and all kinds of cool stuff. And we know that bats know how to do all that, right? I mean, you can watch a bat fly around in the night and you see that they are remarkable in their ability to change the trajectory very quickly. So we chose an animal with these incredible aerodynamic capabilities. And then we did all of our test data on that animal doing nothing interesting, right? So all the learning that we did was for a bat that was just flying in a straight motion, right? Just steady state, flying straight ahead. And so in some ways, we really picked the wrong set of things to look at when we did the design, right? We designed this thing and we tested it on steady flight, right? Easy problems. We just want you to fly up to some altitude and stay at that altitude. Which, if that's really all you want to do, there are much better aerodynamic systems to design than the robot bat. I mean, there are birds with giant wingspans that can fly forever, basically, by gliding. And so we had a real mismatch, I think, in the kind of data that we collected, the animal that we chose to study, and then the test problems that we chose to illustrate our results on. I'm not sure if that answered your question. I got distracted by my own answer. So feel free to follow up if I didn't get the right answer out.
No, I think I got the idea.
Okay.
Thank you, Seth. Don't be shy, ask questions.
There's a question in the chat asking how long can the bat fly?
So we don't know the answer because it can fly. We know that it flies at least as long as the building that we have to fly the bat in. And then we don't know how much longer it would fly if we took it outside. And we never did outdoor flight tests, partially because the bat is not very robust to wind dynamics, right? So some wind will really cause problems for this guy. So all the tests were indoors. And so I don't know. I feel comfortable saying this robot should be able to fly for as long as the battery can make it fly. And that's on the order of minutes, not hours at all, and not very many minutes before the battery runs down.
Thanks. Diego?
Hello, Seth. This is Diego Mercado from CIMAT, Zacatecas. I don't know if you remember me from Micai. Yeah. We're having some good food there.
We have really good food there.
Okay, my question is...
You're making me sad now, Diego.
Come on, you're welcome to Zacatecas whenever you want. My question is if you have tried a very interesting talk. I really like the problem because it seems to be very challenging, right? My question is if you have tried to perform some hover flight. We saw some videos with the bat hovering, like almost staying in place. And I feel like if you can do like hover and then transition into some kind of a steady trajectory as you have already, you already can do like very interesting stuff, no?
It's true. So I'm going to show you this video now. So you see the bat. I mentioned if you put a lot of sensors on the bat, they don't want to fly. On the left is the bat with a sensor pack. And he doesn't want to fly. But if you put something on the ceiling that is delicious enough, he will fly. And so this is a case where the bat's going to fly up to the ceiling and try to eat the delicious food. And the reason I'm showing you this is the hovering behavior is so much more complicated than the steady flight behavior, right? If you look at the way the wings are folding, but also the pronation angle of the wing, how the wings bend forward and backward as he's flying. Our mechanical system doesn't have that degree of freedom as an actuated degree of freedom. And so I believe our mechanical system does not have the capability to hover. It has the ability to do some rapid maneuvers. So we did some like rapid diving maneuvers. I don't know if I have any videos in this PowerPoint presentation that show some pretty agile responses. But in the end, I think it's not necessarily so impressive to show the diving maneuver and to brag about, look, we can make our robot fall out of the sky faster than your robot can fall out of the sky. I'm not sure that that's something you really aspire to do. But that's about the most complicated kind of maneuver that we had that's really fast and agile. We can do turning maneuvers, but they're more graceful, slow kind of turning maneuvers over time. And we have not managed to make this mechanical system hover.
Okay. Yeah, thank you.
Sure.
Some other question or comments?
I have one while other people think about it. Well, you kind of already answered it. I was wondering about why should SPAT. It seems like a popular choice for this kind of work, but I don't know. It also seems kind of like a difficult animal. I'm sure there are easier options, or what other ones did you consider, or why was it so obvious to go for SPAT?
Sure. In fact, this question, this is a question that when I answer it, I think is when I stop talking about engineering and start giving you advice for your career. And so the reason we chose the BAT, there are 2 or 3 reasons. The first reason is this. If you want to do biologically inspired robots, you should not do snakes because how he chose it already does snakes really well. Right? You shouldn't do the cheetah because Sang-Bae Kim already does the cheetah really well. You shouldn't do a fly because Rob Wood already does the fly really well. And you start crossing off the list all the animals that somebody already does really well, and bats are still on the list at the end. So that's one reason. The second reason, Sunjo met Kenny and Sharon at a conference and saw what they were doing. And so the second reason is we had access to some collaborators who were just spectacularly good on the biology side, and even on the engineering analysis of the biological structure of the bat. And so we collaborated with them on the proposal that got funded, that paid for this work. So we didn't have enough money to just go out and design bat robots, right? That's expensive. So we wrote a proposal to the National Science Foundation, and Kenny and Sharon were co-PIs on that proposal, which made it really strong because the stuff that Sunjo brings from the dynamics and the control side and the stuff that Kenny and Sharon bring from the biological side integrated together is really a compelling story. So another reason to choose this animal was because we had collaborators that were experts. Why did I get involved? Because I just think it's really cool. That's the depth of my scientific introspection about why the bat robot is what could be more cool than a bat? Of course, I want to join that project. So I joined that project, you know, basically based on that. We tell a story. I think we don't worry about telling it anymore, but we used to tell the story about how this kind of robot is much more useful than something like a helicopter robot or a quad rotor robot. It's very quiet. It can maneuver. The maneuvering capabilities should be a lot better than a quad rotor, and it's not dangerous at all. Right? If the bat robot flies into your head, it's not fun, but you don't bleed. There's no injury. If a quad rotor flies into your head, it can be really dangerous depending on the system that you use. And so we had a story about construction sites and using bat robots to perch in the construction as it's being built to keep track of dangerous situations for workers. One of the people that collaborated with us was from civil engineering, and he's an expert on this kind of stuff. I was really surprised when I learned how many people die every year working on construction sites. I thought that the humans had advanced beyond that. I thought we could build giant buildings without killing people. And the answer is no, we kill a lot of people in construction every year. And part of the reason that people die on construction sites is because things happen that they are not aware of. They're not paying enough attention when the crane moves overhead and drops something on them. And so, so having a robot that's able to dynamically fly around, perch on the steel infrastructure, for example, and keep an awareness of what's happening at the work site that can be used to inform the workers when they're in danger. That was also part of the motivation. So that's like half a dozen reasons that we chose the bat. Yeah, so I'll stop there.
Thanks, that's very insightful. Can we address this last one so we don't steal too much of your time? There's somebody asking about the wing material.
Oh, so yeah, the wing material was in fact specifically designed for this bat. It had to be, there were a few characteristics. It should be really strong. It should be really flexible. It should be really lightweight and really thin. And so that's what we said to the material science students, and they used a silicon gel. And the way they make it is really cool. You use actually very heavy and very smooth stones. And you put the material on one stone, you put a big stone on top, and it flattens it out, and you cure it over time. But it was a special purpose design. We tried a number of off-the-shelf products, and none of them had the capabilities that we wanted them to have with the same lightweight structure and the same strength.
Thanks very much.
Sure.
Dr. Rafa?
Yes, thank you very much, Seth. It was a great talk. We really appreciate your time.
All right, it was delightful to join you even remotely in Mexico.
Thank you. So we will have another talk tomorrow from Professor Waltelio Mayol from the University of Bristol. So you are invited. Tomorrow is at 1 p.m., I think, right? And let me switch to Spanish. Recuerden que estamos abriendo una maestría en robótica en CIMAT. Si conocen interesados, por favor, háganle saber del programa. Muchas gracias a todos. Thank you very much. See you.
See you.
Thank you.
Thanks.
Thank you. Bye.